Everybody. Today we will look at the characterization of compactness in metric spaces. Since this video is somehow incomplete, it is only a preliminary version that will be updated later. So a topological space E is said to be compact if from every open cover you can extract a finite subcover. So let me draw your attention to the important case where E is a subset of a topological space. So let us, for example, take a closed subset of R2. The open subset of E are in fact inherited from those of R2 by simply taking the intersection with E. So U is an open subset of R2. So if I take a disjoint open subset, its intersection with E is the empty subset. So the empty subset is an open subset of E. If I take an open subset that is included in E, its intersection is itself, so it is an open subset of E. And now you see that with this kind of open subset, you will never be able to cover a point that is in the boundary. So in fact, you have to take into account open subsets of R2 that are not totally included in E, and when you take the intersection, it will contain points that are in the boundary. So this intersection is not an open subset of R2, but it is by definition an open subset of E. So with this kind of open subset, you can cover E, and it is compact if from every open cover you can extract a finite subcover. So now if E is a metric space, so in this video we will admit that it is compact if and only if it is sequentially compact, which means that from every sequence with value in this compact set, you can extract a convergent subsequence, and the limit will also be in the compact set. So second notion, a metric space is said to be compact, precompact, or totally bounded if for all epsilon strictly positive, you can cover it with finitely many balls of radius epsilon. So this is similar to the general definition. And a metric space is said to be complete if every Cauchy sequence converges. Now the theorem, page 32, states that a metric space is compact if and only if it is precompact and complete. So one can understand this as a generalization of what you have for finite dimensional normed spaces. So when the field itself, so R or C, are themselves complete metric space, the finite dimensional spaces, vector spaces, are also complete. And when you have a subset of a complete space, then it is complete if and only if it is closed. And you also know that a subset is compact if it is closed and bounded, if and only if. But in the general case, so for example, if you have an infinite dimensional space or a more general metric space that is not even a vector space, you only have the inclusion, assuming that the compact set is Hausdorff, which in the French literature is assumed that the compact space are also Hausdorff. You only have this implication, so you always have this implication. A compact set is closed and bounded, and you see that what you are missing to have the converse implication is this stronger property of being precompact. So let us show that if you are precompact, you are bounded. So if you are covered by finitely many balls of finite radius, so any 2 point will have a finite distance. So if you are precompact, then you are bounded. Let us now give an example of a bounded set that is not precompact. So for example, the unit ball of an infinite dimensional Hilbert space. So let us assume that we have an orthonormal basis, so vectors of unit 1 that are orthogonal. So the distance between each vector is square root of 2. And I will start to cover it with balls of radius epsilon smaller than square root 2. So for each endpoint of the unit vectors, I add a ball with center the endpoint and radius epsilon. So this will not cover the whole ball. So for every point that is in the ball but not covered, I also add another open ball with the same radius. So you see that if this center is not in this ball, then symmetrically this point is not in this ball. So the consequence is that the endpoint of the unit vectors, they are in fact only covered by the ball with center itself. And because there are infinitely many orthogonal directions, you see that from this open cover, you will not be able to extract a finite cover. So here's an example of a bounded subset that is not precompact. So let us now prove the first implication. So if E is compact and you consider the open cover by balls of radius epsilon strictly positive with center x for every point x in the space. Because E is compact, you can extract a finite subcover. So you do obtain a finite cover by open balls of radius epsilon, and this is true for all epsilon. So if you are compact, then you are precompact. Let us now show that if you are compact, then you are complete. So we take a Cauchy sequence with value in the compact set, and we use the fact that a compact set is compact metric space is sequentially compact. So from this sequence, you can extract a convergent subsequence. So here we use a strictly increasing function from n to n to denote the indices of the subsequence. So the first line, I write the fact that this subsequence is convergent. And here in the second line, I write that this sequence is Cauchy. So let us now check that this whole sequence is convergent to x which is the limit of the subsequence and which is in the compact set. So let epsilon be strictly positive and take epsilon 1, epsilon 2 equals half of this epsilon, and look at the distance of a point xk to the limit. So here I will introduce a point of the subsequence, a term of the subsequence, and if I take k and phi n such that they satisfy this property from the Cauchy sequence, so they have indices greater than this rank, the distance between these two terms is smaller than epsilon 2, so equal to epsilon over 2. And here, if I take n great enough, so large enough, so such greater than n1, the distance between this term of the subsequence and x will be smaller than epsilon 2. So all in all, we have that for all epsilon, the distance between this and the limit is smaller than epsilon. So to summarize, if we have a Cauchy sequence that admits a convergent subsequence, then the whole sequence is convergent. So conversely, if I have a precompact set that is also complete, then we will show that it is sequentially compact. So this proof is in fact the same as that for closed and bounded interval of R. So the Bolzano-Weierstrass theorem proof. So we take a sequence and we want to show that we can extract a convergent subsequence. By precompactness, you can cover E with finitely many balls of radius 1. A sequence has infinitely many terms, so one of the ball will contain infinitely many terms, and we can define the subsequence whose terms are inside this ball. And again, this ball is a subset of the precompact space, so it is itself precompact, and so we cover it with finitely many balls of radius 1/2. And so we can extract again a subsequence of the subsequence. So here, if you have a confusion, you may have a confusion on the order of composition when you want to extract a subsequence. But what you can see is that if you precompose on the right, this set is included in this set phi 0n. But if you precompose, so let us take an easy example. Imagine that it is the even term. But if I compose on the right, and let us imagine that this function is just, they all have to be strictly increasing. But if we take this and we compose on the right, phi1 of 2n, it will be of the form, it will be descent 2n plus 1. So you see that if I compose on the right, I can obtain a subset of indices, but if I compose on the left, I can modify this space. So when we take a subsequence, we can write it as a precomposition by a strictly increasing function, but on the right. So I continue to do this. So at every step, I choose a subsequence of the subsequence, and they are all included in a bowl with smaller and smaller radius. So what I get at this moment is only a family of subsequence, but what we want is a single subsequence. So the Cantor diagonal argument can be understood as follows. So we have our first subsequence that is included in some bowl, so BA0, radius 1. Here I write schematically the second subsequence of the subsequence. It is included in this intersection, and so on, so forth. Included B0, B1. So we choose a first index to build our new subsequence. And here, after we have chosen a term in the first subsequence, we choose a term in the second subsequence, but we want to choose an index that is greater than the first index that we have chosen. And similarly, afterwards, we choose another index from the third subsequence, and we also choose it in such a way that it is greater than the previous choice. So here we have our diagonal term. So more formally, we just pick one index in the first subsequence, and then we consider the indices corresponding to the second subsequence, and we choose one index that is greater than our first choice. And similarly, by induction, if we have chosen the pth term, then we look at the next subsequence, subsequence, and we choose an index that is greater than psi of p. So in this way, we obtain a sequence, and we want to show that this subsequence is Cauchy. So we take epsilon strictly positive and a radius that is smaller than epsilon. So without loss of generality, we consider P and Q greater than N. We can, without loss of generality, could take Q greater than P. So this term is in the subsequence P time, the Pth extraction. And because P is greater than N, it is also in the subsequence extracted P times. So those two terms, they are in this bowl. And so the distance between those two is smaller than the distance from this term to the center plus the distance from the center to the second term. And in the worst case, P is greater or equal to n plus 1. So in the worst case, we have 1 over 2 to the power n plus 1 and 1 over 2 to the power n plus 1. So we'll have 2 times. We simplify and we obtain this condition. So we have shown that our subsequence that we obtain from the diagonal argument is Cauchy. And because the space is complete, the Cauchy subsequence is convergent. So we managed to extract a convergent subsequence. So let us now recall what we have done. So if a space is compact, you see that it is naturally precompact. And to show that it was complete, we just used the fact that a Cauchy sequence which admits a convergent subsequence will converge. So every Cauchy sequence will converge. Conversely, if we have a precompact and complete space with the condition of precompactness, we extract subsequences, and we extract small subsequences that are contained in balls with radius that are smaller and smaller and smaller. And then we obtain a family of subsequence, and with the diagonal argument, we construct a single subsequence. And this subsequence will be Cauchy. And then by completeness, this subsequence will converge. So from a sequence, we extracted a convergent subsequence. So thank you for your attention.